Okay, 4.2, covalent bonding. Nice little diagram you might want to copy down. This is hydrogen with just one electron, so it has one electron in its 1s orbital, half filled. But by two hydrogen atoms having their half-filled s orbitals overlap with one another, they share electrons, thereby filling that 1s orbital for both. And we represent that with a dash. Sometimes you'll see two dots to represent both electrons, but that means the same thing. We'll use the dash. A sharing of electrons, a covalent bond. Covalent bonds, the sharing of electrons between atoms. The electrostatic attraction between a pair of electrons and positively charged nuclei. So both atoms that are sharing electrons have a positive nucleus, of course, and they're both attracted to those pair of electrons equally.
Atoms have three distinct electrostatic interactions with each other. The electrons repel. Similarly, the nuclei repel each other. Finally, the electrons on each atom are attracted to the nucleus of the other atom. When this attractive force is greater than the combined repulsive forces, a chemical bond forms.
General rule, a compound is covalent if it contains only nonmetals. A molecule is an electrically neutral group of two or more atoms covalently bonded. So you might want to jot down a few of these examples. Carbon dioxide, boron trifluoride, this is called benzene, hydrocyanic acid, water. Covalent bonds are directional, meaning the atoms have specific orientations in space relative to one another. As a result, molecules have definite shapes. Now we'll be getting to the Vesper model that determines molecular shapes, not today, but later on in this unit. And these are a few of the shapes that you learned last year: linear, trigonal planar, bent, tetrahedral, trigonal pyramidal. Now these last two here is something that you'll learn in IB Chem 2. To classify bonds, compare the electronegativity values between bonding atoms. So it's the difference. So it's not the electronegativity value, it's the difference in electronegativity value between the bonding atoms. Okay. If it's less than 0.3, then it's referred to as being nonpolar covalent. A good analogy, it's like playing tug of war with somebody who's almost equally as strong as you. It's one person is not going to pull any harder than another. And that's what we mean by a nonpolar. The difference is less than 0.3, then both atoms have a very, very equal attraction for the shared pair of electrons. If it's between 0.3 and 1.7, then it's polar covalent. And this is like playing tug of war with somebody who's substantially stronger than you, but not so strong enough that it can rip the rope away from you. So one person has much more control over the tug of war than the other. So this is polar covalent, and the difference in electronegativity between the atoms between 0.3 and 1.7. If it's greater than 1.7, then it's like playing tug of war with somebody who you just don't have a chance. They're just going to rip the rope right out of your hands. And that's ionic. So one element is so much more electronegative than the other that it's just going to take ownership of the electrons. Okay, now I'm going to show you a video, a IB review video, and he's going to be using this table to discuss the differences in electronegativity. This is from the IB data booklet, and the electronegativity value is in the lower center of each box. Okay, so let's watch that video.
Is it ionic? Well, there's two ways to tell if a compound's ionic: from the periodic table or electronegativity values. This is copyright of the IB. IB, I mean you no harm. I can't even spell baccalaureate. Is it two L's? Is it two C's? I don't know. Okay, electronegativity. That is defined as an atom's ability to attract a bonding pair of electrons. So fluorine has the highest electronegativity of 4, and that loves electrons more than any other element. It has the highest electronegativity. I still think of it after all these years as electron love. Francium has the lowest electronegativity, and that hates electrons more than any other element. Now you can't say hates, you can say it has the lowest electronegativity. You can't really say hates. So if I was to mix francium and fluorine together, the valence electron, the one valence electron on francium, which is an electrophobe, will be transferred to the fluorine, which loves electrons, leaving behind a positive francium ion and a negative fluoride ion. And there you go, that's ionic bonding. So francium and fluorine have the biggest difference in electronegativity. So they're going to be the most ionic. The biggest electrophobe, the biggest electrophile in terms of their electronegativity. Now cesium isn't quite such an electrophobe, doesn't have quite such a low electronegativity as francium, but electrons will still transfer to fluorine. And barium is still electrophobic enough compared to fluorine that electrons will transfer. Niobium isn't quite such a hater, a disliker of electrons as the others so far, but the electrons again will still transfer. Now you can see that as we're bringing these circles closer together, their electronegativity difference is going to be less and less. Now for niobium and oxygen, the electrons are only just attracted to the oxygen from the niobium. So it's only just an ionic bond. So the distance between the circles is important. If they're very close, the electronegativity difference is going to be low and they're going to share the electrons. If they're very far, then the electronegativity difference is going to be big and they're going to make ionic bonds. So the closer the metal and the non-metal are, the less ionic it is. So let's see if we can find a metal and a non-metal that's covalent. Yeah, copper and phosphorus, they're close enough that the electrons won't transfer from copper to phosphorus. They're actually going to share them. It's going to be a covalent bond. So let's zoom in a bit more on the periodic table. So if the electronegativity difference is greater than 1.7, it's ionic. There's a big difference in electron love, if you will. And if it's smaller than 1.7, it's covalent, or the bond is covalent. Now 1.7 is a bit arbitrary. I've taught in different countries. Some other countries say it's 1.9, 1.8, but the IB seems happy with 1.7. So looking at calcium and chlorine, calcium chloride, the difference is 2.2, so that's big enough difference to be called ionic. Scandium sulfide, well, the difference there is 1.4 to 2.6. No, that difference is less than 1.7, so scandium sulfide is covalent. Even though it's a metal and a non-metal, still covalent. What's the furthest we can go here apart would be rubidium and helium. No, helium doesn't react. It has no electronegativity. So it's got a full outer shell, it's completely inert, so it has no En value. But rubidium fluoride, that's the most ionic compound that we can make using this segment of the periodic table. So go and ask it. You know you want to ask it. What's the question? Okay, so what if the difference is exactly 1.7? Well, there are cases of that. Is it ionic? Is it covalent? Well, it's right in the middle there. For argument's sake, you could say, well, let's go to another significant figure and then you can work it out. But really, it's just a spectrum. You could perhaps see if it as a solid, it was an insulator, but if you melted it or dissolved it, it was a conductor, then you could say, well, maybe it's ionic. But that's probably beyond what you have to know.
When we have a polar covalent bond, we use the Greek letter delta or an arrow to represent the bond polarity. So let's look at the bond between carbon and fluorine, for example. We're not looking at a molecule, just the bond between these two atoms. When we look up the electronegativity values, we can see the difference between the two is 1.4, so that falls into the polar covalent category. So it's an unequal sharing of electrons, and because fluorine is more electronegative, you have more electrons over on the fluorine side. And so we can represent that using the delta symbol. Delta negative is the side that has more electrons. Electrons are negatively charged, so more electrons, the electrons are being shared are more over on this side, so this side is slightly partially negative, and this side by default is partially positive. Now we can also use an arrow to represent that, and the arrow is always pointed towards the more electronegative element. So you'll see both an arrow used or the delta symbols. Naming binary molecular compounds. This is fairly easy. I'm sure you'll remember this. We use prefixes. So 1 through 10, and the prefixes mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. So let's do some practice here. You might want to pause the video and try to name these yourself, but I will do it in 3, 2, 1, now. All right, so the first one carbon and 1 oxygen. And this is carbon monoxide. Now, the only exception to using the prefixes is the first element. If the first element is just 1, we don't say mono. But as you can see, if the second element is 1, we do say mono. So this is carbon monoxide, not monocarbon monoxide. But all the other, if there's more than 1 of the first element, as we'll see in a second, we always use the prefixes. Now, we always end, just like we're an ionic compound, we always end the name with IDE. So whatever the second element is always ends in IDE. And I forgot to point out, binary molecular means just 2 atoms. You can have molecules, certainly with more than 2, but the naming gets a lot more complex, and is mostly going into organic chemistry, which will be our last unit. But right now we're just interested in naming binary molecular compounds, compounds that are made up of just 2 different atoms. Okay, the second one is carbon dioxide, and then dinitrogen trisulfide. Notice that they all end in "ide." Make sure you don't end the first name with "ide." Sometimes kids will go "ide crazy" and like this, name this dinitrogen ide trisulfide. No, just "ide" on the second name. And then the last one, diphosphorus pentoxide. Now notice that pent, it's actually, the prefix is actually penta, but we don't say pentaoxide, we just say pentoxide. So sometimes we drop the vowel on the prefix. Don't get overly concerned about that, just be aware that that is the case. That also occurred for monoxide, so it's mono and then oxide, but we don't say monoxide, we just say monoxide, so we dropped one of the O's. That's it for naming. Lewis structures. The use of dots and dashes to represent the valence electrons of an atom, ion, or molecule. So an example. So we'll be learning how to draw Lewis structures. Every dash represents a pair of electrons. So this is a double bond, so that's 2 pairs of electrons. So that represents 4 electrons there. And you can see every atom is surrounded by 8, and that's kind of the name of the game. Every atom needs to obey the octet rule by sharing electrons. Remember, the octet rule, atoms tend to lose, gain, or share electrons. So here, we're sharing. Okay, now these are the steps to draw a Lewis structure. And in doing Lewis structures and drawing Lewis structures, I will be following these steps. Total all the valence electrons and charges. Connect all atoms to a central atom. Add dots to complete an octet around every atom connected to a central atom except hydrogen. Add dots to complete the central atom's octet. And if too few electrons are available, we use multiple bonds. So when I'm going to be doing a bunch of Lewis structures here in a minute, so when I'm doing that, I'll be referring to these steps. So we're just going to do it in order over and over again, as you'll see. Okay, now the honk rule is a really useful tool when you're drawing a Lewis structure. However, the word rule is a bit too rigid. It's really kind of a generalization. It's kind of a guide. If you have a choice of different ways to go with the honk rule. It's almost always correct. And what the honk rule is if we just arrange the elements in order of the name honk, so hydrogen first, or hydrogen or halogen first, and then the second is oxygen, the third nitrogen, and the fourth carbon. Well, the ordering tells us the number of bonds each of those elements will usually have. So hydrogen or halogen, so let's let X represent any of the halogens, will have just 1 bond. Oxygen will have two bonds, which could be two single bonds or a double bond. Nitrogen will have three bonds, either three single bonds, a single and a double bond, or a triple bond. And carbon will have four possibilities. Four single bonds, two single and one double, two double, a single, and a triple. So again, when you are drawing a Lewis structure, the honk rule is really a very, very useful tool in determining the structure, as you'll see. Now, when you're done drawing your Lewis structure, it's so easy to make a mistake, but all you have to do, and it's really quite simple, is ask yourself two questions. One, was the exact number of valence electrons used? And two, are all atoms except hydrogen surrounded by an octet? If both of those statements are true, then you have a correct Lewis structure. And I guess I forgot to add that here. So if the answer to both of these questions is yes, then your Lewis structure is correct. If not, then it is not correct, even though it may look correct. So an example, let's look at the nitrate ion. Now you might be tempted to think that this is a correct Lewis structure for the nitrate ion. Every atom is surrounded by 8, but it is not correct. The correct Lewis structure has a double bonded oxygen. Now why that is has to do with the total number of valence electrons. This is 26 electrons, but we only have 24 electrons to build our Lewis structure, which is what we have here. And to be technically correct, when you draw a Lewis structure, as we'll see, if it's an ion, we put it in brackets and indicate the charge. More on that in a minute. Okay, let's do some practice. Start off easy. Water. Okay, so first step is to add together all the valence electrons. So we have two hydrogens, each has one valence electron, and the one oxygen has 6. So that gives me 8 electrons total. Now, of course, those numbers I got right from the periodic table. Hydrogen has 1 valence electron, oxygen has 6 valence electrons. Next step is to connect all the atoms to a central atom. Now, when you do this, the guiding principle that's almost always going to steer you in the right direction is symmetry. We always want to spread things out as evenly as possible. If you were to put the hydrogen in the center and the oxygen on the end, you can see it would be lopsided. You'd have two hydrogens in a row and oxygen on the end. Also remember the honk rule. The honk rule tells us that oxygen will have 2 bonds and hydrogen will have 1 bond. Now, as we'll see, there will be exceptions to the honk rule except for hydrogen. Hydrogen will only have that 1 bond, and that is it. You can kind of think of it like the one-armed element. Hydrogen, if ever you see a Lewis structure, try to build a Lewis structure where you have more than a single dash on the hydrogen. It's going to be incorrect. Now, the oxygen needs to be surrounded by 8 electrons. Currently, it has 2 bonding pairs of electrons, or also referred to as shared pairs of electrons. Now remember, the dash here represents a sharing of electrons. You have a half-filled s orbital from the hydrogen, and you have a half-filled p orbital from the oxygen. And those 2 half-filled orbitals merge together to share electrons to form a covalent bond. Oxygen has 2 half-filled p orbitals, and so it can have 2 bonds, whereas hydrogen only has the 1 half-filled s orbital, so hence it can only have 1 bond. Now, oxygen needs to have 8 electrons around it to obey the octet rule. Currently, it only has 4 electrons, so what we need are 2 more pairs, and these pairs are non-bonding pairs or lone pairs. I prefer that term, lone pair. Lone pair or non-bonding. Now remember, oxygen, if we were to look at the orbital diagram for the valence electrons for oxygen, we would see that we would have the S would be full, and the P, you would have 2 filled orbitals and 2 half-filled orbitals. So here we have our 2 filled orbitals, the 2 electrons, and the 2 half-filled here. Okay, so now we've used a total of 8 electrons, 2, 4, 6, 8. It doesn't matter whether it's a lone pair or shared pairs, it's 8. And so that is the number that we need. Every time you draw your Lewis structure, you need to make sure that every atom is surrounded by 8 electrons except for hydrogen, and that you've used exactly the number of electrons that you came with. Okay, let's try another one. Let's look at ammonia, NH3. So nitrogen has 5 valence electrons. Each of the hydrogens has 1. So again, we have 8 electrons. Connect all the atoms to a central atom. Again, symmetry. And remember, the Honk rule tells us that nitrogen will usually have 3 bonds, which is what we have here. Now I have 2, 4, 6 electrons around the nitrogen. They're all bonding pairs of electrons or shared pairs of electrons. So we need 2 more. And so we'll have 2 or 1 lone pair on the nitrogen. So now we have 2, 4, 6, 8, a total of 8 electrons. This is what we need. And so we now have a completed Lewis structure. Okay, let's try another. Let's try ammonia. I'm sorry, ammonium. Ammonium has a positive 1 charge on it. When I add together all of the electrons, so nitrogen has 5, you have 4 hydrogens, each has 1. Now that's how many electrons we would have if it didn't have a positive 1 charge. But because it has a positive 1 charge, we're going to remove 1 electron, which again gives us 8. Now, when we draw our Lewis structure, we'll see that we're going to violate the Honk rule. We'll have to, because the nitrogen is going to have to bond to all 4 hydrogens. So this is a case where the Honk rule doesn't work, because the Honk rule says nitrogen is going to have 3 bonds, but here we have 4. So there will be exceptions. Don't go to the exceptions unless nothing else works. The Honk rule almost always works, but this is a case where it doesn't. Now, when you have a Lewis structure that has a charge, or you're doing it for an ion, you need to put the entire Lewis structure in brackets and indicate the charge. This enables the reader to quickly, at a glance, see that in order for the Lewis structure to exist, we needed to, in this case, lose 1 electron, hence the positive 1 charge. Okay, let's try another. Let's try carbon tetrachloride. Carbon has 4 valence electrons, and each of the 4 chlorines has 7 valence electrons. So that gives us 32. Connect all the atoms to a central atom. Again, think symmetry. So we're going to have all 4 of the chlorines bond to the carbon. And then, to complete the octet for each of the chlorines, we're going to need to have 3 lone pairs. All 4 of the chlorines. Now the carbon, remember the Honk rule, carbon will have 4 bonds around it, which is what we have here. So carbon has 8 around it, each of the chlorines has 8 around it. Let's double check that we've used the right number of electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We've used the right number of electrons, and so this is a correct Lewis structure. Now, so far, things are falling into place pretty easily, but that won't always be the case. Let's look at the sulfite ion. Sulfite ion has a -2 charge on it, so let's add everything up. Sulfur has 6 valence electrons. You have 3 oxygens. Oxygen also has 6 valence electrons. Oxygen and sulfur are in the same family. Now, the -2 charge here means that you have 2 more electrons. Without the -2 charge, you would have 24 electrons, but the -2 means that we have 2 more electrons. which gives us 26. Okay, now when we draw the Lewis structure, we'll have sulfur in the center and then oxygen bonded to it. Again, think symmetry. Now remember, the Honk rule tells us that oxygen is going to have 2 bonds, and we can see that that's not going to be the case here. Again, I'm showing you, at various possibilities. The Honk rule almost always works, but in this case, no. The oxygen can only have 1 bond. Now let's complete the octet around the outer atoms. So always complete the octet on the outer atoms first. And you'll see why in a few minutes. Okay, so now every oxygen is surrounded by 8, and I've used so far 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I have 2 more electrons, which is good because the sulfur right now only has 2, 4, 6 electrons. It needs 2 more. So now I've used the 26, and every atom is surrounded by 8. So what I'm doing here is a really good idea when you do your Lewis structure. Just circle every element and make sure that the count is 8. And then it is an ion, has a -2 charge on it. So like the ammonium before, we need to put it in brackets and indicate the charge. So this tells our reader that this Lewis structure, in order for it to exist, needed 2 more electrons. Okay, let's look at another one. In this one, we're going to have a little bit of a problem. This is carbonate. Now, it looks very similar to sulfite, but carbon is not in the same family. It only has 4 valence electrons. So when I add together all of my electrons, I'm going to have 24 rather than 26. So I'm going to follow the same steps, connect all the atoms to a central atom, carbon in this case. Complete the octet on the oxygens here. Now, before I put in the dots on the carbon, a couple of things to consider. Remember that carbon should have 4 bonds around it, but it only has 3. And so if I put a pair of electrons here, a lone pair, well, then that wouldn't obey the Honk rule. And a little bit later in your notes, we'll talk about carbon. Carbon is it's kind of like hydrogen, always will have just 1 bond. Carbon will always have 4 bonds. Whereas the Honk rule here, oxygen, usually has 2 bonds. Here it only has 1 bond. So the other elements, there's a little bit more wiggle room, but not with carbon and hydrogen. They're pretty strict. So in order to have carbon surrounded by 8, I need to bring in what we call a multiple bond, a double or a triple bond. Now, right now, I've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons, and that's all that I have, is 24. So I wouldn't even have the electrons if I wanted to put in 2 electrons here or a lone pair here. I couldn't do that because I don't have them. I've run out of electrons. So what I'm going to do, and I'm just doing this for instructional purposes right now. You don't need to do this when you're drawing your Lewis structure. I'm going to take one of the lone pairs off of one of the oxygens, and it doesn't matter which one, and I'm going to turn that into an additional shared pair between the carbon and the oxygen. So let me rewrite that down here. So I have carbon now with a double bonded oxygen, and the others will be single bonded. And then I'll complete the octet on the oxygens. But on the double bonded oxygen, it already has 4 electrons or 2 pairs, so it just needs 2 more lone pairs to complete its octet. So now every atom is surrounded by 8. The oxygen is surrounded by 8, and the carbon is surrounded by 8. So you can see that we haven't lost any electrons or gained any electrons in doing this. We simply made one of the lone pairs an additional shared pair. So now I've used 24 electrons, which is the number that I need to use, and every atom is surrounded by 8. Again, it's an ion with a negative charge, so I'll put it in brackets and indicate the charge. Try another. Okay, now let's look at carbon dioxide. So 4 valence electrons for the carbon, 2 oxygens, each have 6, and that gives me 16 electrons to build my molecule. Connecting the oxygens to carbon, and then completing the oxygens octet. Now remember, I'm just following the steps here. So if I seem like I'm going too fast, just kind of go back to the steps that you wrote down. Step 1, add together all of the valence electrons. Step 2, connect all the atoms to a central atom. Again, think symmetry. 3, complete the octet around the outer atoms by adding lone pairs of electrons. And then complete the octet of the central atom. But if you don't have sufficient electrons, then we need to have multiple bonds, which is the case here. We've already used up 16 electrons, 2, 4, 6, 8, 10, 12, 14, 16. So I have no more electrons to put any dots around carbon, and carbon only will have 4 bonds anyway, so we know that that's not going to work. So, like carbonate that we just did, I'm going to take one of the lone pairs on the oxygen and make it be an additional shared pair between it and carbon. And I'm going to do that the same to the other oxygen, which gives me carbon with 2 double bonded oxygens. Completing the oxygens octet. And there you have it. Every atom is surrounded by 8, and I've used exactly the right number of electrons, 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16. So that's the name of the game. Play around with the bonding however you might need to so that you've used exactly the number of electrons that you came with. Okay, now, let's look at something that might throw you off a little bit. This is hypochlorous acid, HClO, and this is the way it's typically written. If we add together all of the electrons, hydrogen has 1, chlorine has 7, oxygen has 6, that would give me 14. Now when you go to draw the structure, you would think that chlorine would be in the center. It's the way it's drawn here. But remember the honk rule, and this is where the honk rule really is quite handy. If you have a couple of choices on how to do something, always follow the honk rule. Chlorine is a halogen. It will have 1 bond, almost always just has 1 bond, whereas oxygen will almost always have 2 bonds. So rather than writing it so that chlorine is in the center, I'm going to draw it with oxygen in the center, even though the formula is a bit misleading. So oxygen is going to be in the center, and then chlorine, and then hydrogen. Both. So now, remember the honk rule, hydrogen or halogens will have 1 bond, and oxygen will have 2 bonds, and then they complete the octet. On the oxygen, oops, I should have done the octet on the chlorine first. So now I've used 14 electrons, 2, 4, 6, 8, 10, 12, 14, and every element obeys the octet rule except for hydrogen, and we've also obeyed the honk rule. Now you could draw the Lewis structure with the chlorine in the center, but that's not the way it is. Chlorine only has 1 half-filled p orbital, whereas oxygen has 2 half-filled p orbitals. Okay. Let me try hydrocyanic acid. You'll learn the names of these acids later on. Actually, it's something you learned last year you may have forgotten. Okay, now for this, hydrogen has 1 valence electron, carbon 4, nitrogen 5, so that gives me 10 electrons. So I'm going to bond the hydrogen and to the carbon and the nitrogen. Now to complete the octet on the nitrogen, and this, again, I'm going to have a problem here, so this will be revised in a second. If I complete the octet around nitrogen, that would give me 2, 4, 6, 8, 10. And so the nitrogen is good, the hydrogen is good, the carbon not so much. Carbon needs to have 8 electrons around it as well. So in this case, I'm going to take 2 of the lone pairs on the nitrogen and make them additional pairs between it and the carbon. So this means that that carbon and nitrogen are going to have triple bonds between them. Okay, so now I've used 2, 4, 6, 8, 10 electrons, and every atom except hydrogen is surrounded by 8. Carbon has 4 bonding pairs, nitrogen has 3, and 1 lone pair. Nonetheless, each has 8 around it. Okay, now also add to your notes that only 3 elements can triple bond. Only 3 elements can triple bond. And they are carbon, nitrogen, and oxygen. So as far as triple bonds go, those are the only 3 that are capable. Why? Well, if you look on the periodic table, those are in period 2, and they're very small. So the electrons, the orbitals, can literally wrap around the nucleus in order to form those bonds. But when you go down to higher periods, you have bigger elements, and the orbitals aren't able to wrap around. It's kind of like you can wrap your arms around a small tree, but if it's a big tree, you're not going to be able to wrap your arms around it. So triple bonds are limited to relatively small elements, specifically these 3. As far as double bonds, many elements can double bond. Even the halogens can double bond, but you're not going to see that for a while. Okay, our exceptions to the octet rule. As we've already discussed, hydrogen will have only 1 pair of electrons surrounding it. So it just has that 1 dash, like the one-armed element, as I said. If ever you see a dash and dots, or a double bond or triple bonds, or anything other than a single dash, it's going to be wrong. So please don't do that. So for example, if you're asked to draw the Lewis structure for hydrogen chloride, this would be its Lewis structure. Of course, chlorine would obey the octet rule, but not hydrogen. Boron will usually only have 3 pairs of electrons surrounding it. So for boron trihydride, you might be tempted to put a couple of dots on the boron as well, but that won't be the case. Beryllium, even though it's a metal, can form covalent bonds. As you saw in the IB video, just because it's a metal doesn't mean that it's completely excluded from forming covalent bonds. They usually don't, but it can occur if the difference in electronegativity is less than 1.7. Beryllium, if it does form a covalent bond, it'll do so having only 2 pairs of electrons surrounding it. So just that, no dots. So for example, beryllium difluoride, or it would be beryllium fluoride, then this would be its Lewis structure. Just 2 dashes, 4 electrons, and that's it. Sulfur and phosphorus will occasionally have more than 4 pairs of electrons by using their empty d orbitals. This is called an expanded octet. So let me show you a couple of examples of that. Phosphorus and sulfur are exceptions. Again, I'm just picking a simple example. So I'll say phosphorus pentahydride. So phosphorus has 5 valence electrons, and each of the hydrogens have 1, so it gives us 10. So when we draw our Lewis structure, we'll find that the phosphorus is going to have to bond to all 5 of the hydrogens. Remember, hydrogen can only have 1 bond, and so it would look something like this. 5 hydrogens. Sulfur can have 6 bonds around it. Let's look at sulfur hexahydride. So we have 12 electrons. And for it, we'll have 6 bonds on the sulfur. Now, don't go running to these exceptions, boron before or phosphorus and sulfur here, to build your Lewis structure. This would be only when nothing else works. Let's look at oxyacids, which the structure for an oxyacid is just slightly different than you would expect it to be. However, it's an easy fix. Now, what an oxyacid is, it's an oxyanion, like phosphate, nitrate, sulfate, that has hydrogen bonded to it. And they will always have the acidic hydrogen bonded to an oxygen. So let me show you a few examples. Okay, let's look at oxyacids. Now, oxyacids are the case where the hydrogen will be bonded to an oxyanion. And just to kind of remind you what an oxyanion is, it's simply a polyatomic ion that has oxygen in it. So nitrate, sulfate, phosphate, all of these are oxyanions. If I was to add a hydrogen to these, I would end up with nitric acid, sulfuric acid, phosphoric acid. And the main point of all of this is that when you draw your Lewis structure for oxyacids, the hydrogen will not be bonded to the central nonmetal, nitrogen, sulfur, phosphorus. It'll be bonded to the oxygens. Okay, so let's do nitric acid as an example. HNO3. So we have 1 valence electron for the hydrogen, 5 for the nitrogen, 3 oxygens with 6 each, so that gives us 24 electrons. Now, when you go to draw the Lewis structure, we'll put the oxygens on the nitrogen, and it's going to be tempting for you to put the hydrogen on the nitrogen. It would seem like that would be the way it would be. Nitrogen needs 4 bonds, and so why wouldn't we put the oxygen here? Well, that's not the way an oxyacid works. For an oxyacid, the hydrogen will be bonded to an oxygen. Now, it doesn't matter which one you choose to bond it to or how you draw it. It just needs to be bonded to the oxygen. Then we need to complete the octet. However, we'll have a little bit of a problem here. So now each of the outer atoms is surrounded by 8, and we would want to put another lone pair on the nitrogen to complete its octet, except we have now run out of electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We only have 24 electrons. So that means in order for the nitrogen to be surrounded by 8, I'm going to have to take one of the lone pairs off of one of the oxygens and make an additional shared pair, so the nitrogen is going to be double bonded to one of the oxygens. However, when you do this, you're not going to want to pick the oxygen that already has the hydrogen bonded to it. You want to pick one of the other oxygens. So I will take this lone pair here and make it an additional shared pair here. And so rewriting it, I have a double bonded oxygen, a single bonded oxygen that has a hydrogen bonded to it, and then another oxygen. Completing the octet for the oxygens. And that would be it. Every atom is surrounded by 8, except for hydrogen, and I've used exactly 24 electrons. Okay, let's do a couple more oxyacids. About chloric acid and carbonic acid. Now for chloric acid, let me just go ahead and add them together here. It's 26 And over here it'll be 24. Now, when I connect all the atoms to a central atom, I could choose either chlorine or oxygen. Now, remember, symmetry is almost always the way to go. So even though putting chlorine in the center should go against the grain a little bit because it violates the Honk rule, it's the only choice to maintain symmetry. Now again, the Honk rule is really a good map for most Lewis structures, but it's not always the case. So there are exceptions, as you've already seen. So this would be another example of an exception to the Honk rule. Now the Honk rule, really, it's more if you have choices, go with the Honk rule. But if you don't have a choice, which we don't have here, well then, live with it. Okay, so now, because it's an oxy acid, the hydrogen will be bonded to one of the oxygens. Again, it doesn't matter which one I choose or how I draw it. I could have drawn this hydrogen over here, doesn't matter. And then complete the octet on the oxygens. And now, to complete the octet on the chlorine, I need to make sure I have enough electrons. Well, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I have 2 more electrons, and so I can go ahead and put in a lone pair on the chlorine. So I have every atom surrounded by 8. It's an oxy acid, and the hydrogen is bonded to the oxygen. Okay, now for carbonate, now if you want, you kind of have enough, you've seen enough already, you might try to do this one yourself. So why don't you pause the video, see if you can do it, and then come back and I'll walk you through it. And 3, 2, 1, I will walk you through it. So carbon's going to be in the center. And you have 2 hydrogens. Now the hydrogens, you want to spread things out. If you just did it and you put both the hydrogens on the same oxygen, again, you think symmetry, you want things spread out. So if you were to have both hydrogens on the same oxygen, things are kind of lopsided. So I'll put 1 hydrogen over here and 1 hydrogen over here. And then I'll complete the octet on the oxygens. But before I put 2 dots on the carbon, remember carbon is going to have 4 bonds. So if I put dots here, that would be a violation of that. And we don't have 2 more electrons. This is 24 electrons. So in order for the carbon to have an additional bond, or to have 8 electrons, it's going to need an additional bond. It's going to need to have a double bond with one of the oxygens. But when you do that, don't pick the oxygens that already have hydrogen bonded to them. Pick the other oxygen. So this oxygen, one of the lone pairs, will form an additional shared pair with the carbon. So let me rewrite it down here. So now every atom is surrounded by 8, and we've used 24 electrons. Last, let's take a look at carbon. Carbon will rarely have an unshared pair of electrons. But there are 2 exceptions. Both are notoriously toxic. So let me show you those. They are carbon monoxide and cyanide. Both very well-known dangerous substances. They both have 10 electrons to build their Lewis structure, and they both have a triple bond between the atoms. Which means that the carbon needs to have a lone pair on it. So remember that carbon always will have 4 bonds except for these 2 exceptions. It's that lone pair that makes them so dangerous. When you breathe, there's a molecule in your blood that gives it the red color called hemoglobin. in the center of the hemoglobin is an iron ion. And that iron ion is what bonds to the oxygen that you breathe in. The problem is that the iron ion in the hemoglobin in your blood has a stronger attraction for carbon monoxide and for cyanide than it does for oxygen. So when you breathe in, the carbon monoxide or the cyanide replaces the oxygen that you need, and so you quite quickly suffocate, asphyxiate. So hopefully you have a carbon monoxide detector in your home. It has no color, it has no odor, and so it's very important that it's detected before it has a chance to build up. The most common source of carbon monoxide is incomplete combustion. A furnace that's not burning correctly, or a fireplace there's not sufficient oxygen to burn whatever in there, it will produce carbon monoxide. In normal combustion, carbon dioxide is produced. But in incomplete combustion, you have carbon monoxide is produced, so very dangerous. So this is very easy to produce. Cyanide, not so much, so you don't have cyanide detectors. It's relatively rare, but not carbon monoxide. Carbon monoxide is very easy to produce. That's it. End of notes for 4.2.